Hello and welcome everyone. My name is Spitthoff. I'm a PhD student at NTNU in Trondheim, Norway. And I would like to present the work me and my group have been doing on non-isothermal battery modeling. With the transition from fossil fuels to renewable energy sources, reliable energy storage technologies are key. Lithium-ion batteries have become one of the major technologies in many sectors. But there are still some obstacles to overcome when it comes to implementing lithium-ion batteries within large-scale applications like electrical vehicles and ships. So one of the largest problems there is that with increasing battery size, large amounts of heat are generated, especially during intense charging and discharging. And with elevated temperature, problems are imposed. One of them is accelerated aging, as we can see in this diagram here. So the amount of cycles that can be reached until the end of the life of a battery is drastically decreasing when the temperature is increased. In addition to that, the performance of a lithium-ion battery is reduced with increased temperature, and safety problems are imposed like thermal runaway. We know that interfaces play a significant role in some of the major degradation mechanisms in lithium-ion batteries. One of them is unstable and growing solid electrolyte interface, also called SEI layer. So SEI is a layer on the anode material which is needed to prevent the electrolyte from degrading. But when this solid electrolyte interface becomes unstable, which can happen at high temperature, the electrolyte is further degraded. So understanding the heat generation and heat transfer processes in a lithium-ion battery are critically needed for progress. Our aim was to develop a non-isothermal battery model, including coupling of heat, charge, and mass transfer to be able to compute the temperature time profile. Another aim of ours was to look into interface properties and to see how important they are for modeling. So common lithium-ion battery models, thermal battery models, are typically including the same heat generation terms, which are Joule heating and overpotential as irreversible heating terms, and entropic heating as reversible heat generation terms. And entropic heating is commonly included as temperature times the entropy change over the whole cell. So what we are doing in our model is, first of all, we're simplifying the system. So rather than including all the single particles that you have within the anode and cathode material, we're simplifying and saying we have three homogeneous phases, which are on our anode bulk, the membrane with electrolyte bulk, and the cathode bulk, which are separated harshly by two interfacial regions, the anode surface and the cathode surface. We're obtaining our temperature time dependency by solving the local energy balance. And we're obtaining the flux equations using non-equilibrium thermodynamics. And the biggest difference here to the common thermal models we see in literature is that we're including the local effects of entropic heating rather than having the whole entropic heating over the cell. So we're including cooling or heating effects at the interfaces from reversible heat effects, which are also called the Peltier heat. So let's have a look into the equations we obtain. As already said, we obtain our temperature time dependency by solving the local energy equation. And for the flux equations, we include what is commonly seen for the heat flux, the Fourier's law, the mass flux Fick's law, and for the potential, the Ohm's law. But we're not only including those diagonal terms, but we're also including the off-diagonal terms, which are the coupling between heat, mass, and charge. And staying with the Peltier heat effects, we see that the coupling terms between heat and charge consist the Peltier coefficients. So moving on to the interfaces, we define our interface in a way that we have no neutral mass flux over the surface. We also say that all our electrode reactions are happening at the interface, and we treat them as an autonomous thermodynamic system, with fluxes going into the interface and fluxes going out of the interface. And we're balancing around it, obtaining discrete equations for our interfaces, rather than continuous ones as we have for the bulk. So what is already indicated here is that with this discrete treating of those equations, we obtain jumps in our fluxes at the interface. And this jump for the heat flux comes from the Peltier heat at the interface. And the Peltier heat is defined as the heat needed to keep the surface at a constant temperature when 1 Faraday of positive charge is passing it from left to right. The Peltier heat gives us information on heat absorbed or released reversibly at the electrode surface. So as I already said, we consider that all our electrode reactions are happening at the interface, and at the anode surface, this means that we have the neutral lithium going into the surface, and then this has to be equal to the charged species going out of the surface. So what we are modeling for the work we're presenting today is we have a discharge. We're looking into coupled transport of heat and charge, neglecting mass transport for now, even though we already have the equations, but that is part of later work. And we're considering a typical lithium-ion battery material composition with a graphite anode, LiPF6 in ECDEC as electrolyte, and lithium iron phosphate as the cathode material. So as I already said, we have this SEI layer on the graphite anode, and we consider this SEI to be our anode surface. For lithium iron phosphate, it is very common that the particles are coated with carbon to increase conductivity. So we're assuming that our cathode surface consists of carbon. We model this using finite differences, forward in time, central in space, and with the initial conditions that we have the temperature throughout the whole battery equal to the ambient temperature, and the potential in the bulk phases equal to the open circuit voltage of those materials against lithium. For our boundary conditions, we say that the temperature at the boundary is equal to the ambient temperature, which means we consider perfect cooling. This might not be realistic for an applied battery, but as we are mostly interested for now in the interfaces and what is happening there, it's a good simplification. So let's have a look what is happening when we start our discharge. So as we see, we initially start with the temperature throughout the whole battery equal to the ambient temperature. And once we start the discharge, we see that the temperature at the anode surface drops and that the temperature at the cathode surface rises. When we continue this discharge, we see that those temperatures are propagating towards the boundary, and that after a while we see a transitioning towards linear profiles within the bulk phases due to those fixed boundary conditions. But we're not only looking into the temperature profiles over our battery, but also look at the heat flux, the potential, and entropy production, which gives us a good check for the model consistency. When we see that our potential, the heat flux, and the entropy production all give us values that are in the range where we would expect them. So we also looked into changing the current density and see what the effects are there. And as expected, our temperature gradients become larger when we increase the current density. And just to have a rough expectation here, a current density of 30 ampere per square meter would be in a range where we discharge our battery within an hour. So even when we see that our increased current density gives us increased temperature gradients, we see that those temperature differences are still not that large. But we have to consider here that for once we're only looking into 1 minute of discharge, we are fixing our boundary temperature, so we don't allow our battery to heat up as we perfectly cool the battery. And we're only looking into one single cell rather than what we would have in a real application, that we have a stacking of those cells. And with this, the effect that we see would be amplified. And also we would expect to see that within the battery, the temperature in the middle would be the highest, and we have a periodical temperature profile with lower temperatures in the anodes. So as I already said in the beginning, we're very interested to see how important those surface properties are for lithium-ion battery modeling. So we introduced scaling factors for the thermal conductivity of the interface and for the excess density of the interface, and made a small parameter study here. So what we see is that not only define the surface properties, the magnitude of the temperature changes we see, but it also defines the temperature profile in itself and the behavior. So we see how important those surface properties are. But what we see in literature is that it's barely done in experiments looking for those surface properties. We only found one experimental study where we found values for a cathode surface for a different material than what we are looking into, but we still use this to compare to our values. And we end up with a range of power -5 and 5, which is the blue line in this. So this gives us the motivation to continue our research within those surface properties and see how important it is to consider those. So with this, I would like to conclude my talk. We have modeled a time-dependent temperature profile of a lithium-ion battery unit cell. We showed that Peltier heats are needed to find the reversible heat effects local to the electrode surfaces. And we saw that during discharge, the anode cools and the cathode heats. And I'm saying anode and cathode rather than anode surface and cathode surface, because even though we see that those effects are happening at the interface, we always have to be aware of the simplifications that we're doing. We're not having one sharp interface at the anode bulk, but we rather have a surface at every single particle. So a lot of those interfaces throughout the whole anode material. And lastly, we see that surface properties are defining the internal thermal behavior, and it is very important to find those values. With this, I would like to thank my group from NTNU. This is Astrid, Michael, Otne, Signe, Dick, and Marco. And I would like to thank PoreLab for the support. And thank you for your attention.